Hi, I'm Hossein Esfandiari. This is a joint work from, with Dean, Elchanan, and Amin. Um, Probably I don't need to motivate influence maximization. The influence maximization was introduced by Kempe, Queenberg, and Tardush in 2003. And influence maximization, we want to seed some nodes in a network by, say, giving them some coupons or giving them some medications. And we want to have some influence on the whole network. Uh, there are a few different settings to model this. The most common one is independent cascade model, which is the focus of this talk. But there are some other models as well, like linear threshold model. When the influence function is monotone and submodular, there is a 1 minus 1 over E approximation algorithm for the problem, which is basically the greedy algorithm. If you don't know what's monotone and submodular, it doesn't matter. Independent cascade model is monotone and submodular. So if you do greedy, we are going to have a 1 minus 1 area approximation. But these algorithms, like the traditional offline classical algorithms for the problem, requires explicit and complete knowledge of the whole network, right? So we need to know the whole network, and then we can optimize and have 1 minus 1 area approximation. But what if we don't have access to the whole network? Say there is a village and we want to go and do survey in the village to understand the relation between the communities in that village. So we cannot learn the whole network at once, and it's not very cheap to learn the whole network. Or maybe we have a very massive network, like a massive social network, and we cannot deal with the whole network at once. Or we cannot even run an algorithm on a single machine. So algorithms with limited information or algorithms that do not access the whole network and just access a part of the network are both good when we are working in settings that we don't have, that information is costly, and when size of the network is very large. And there are actually a bunch of algorithms that deals with limited information in network for influence maximization, but they're mostly somewhat heuristics. They don't give you some guarantees compared to the optimum algorithm. Okay, let me start with our problem formulation. We are working with independent cascade. In independent cascade, we seed some nodes, and then each adopted node passes its adoption through each edge connected to it with some probability p. Yeah. And we want to have limited access to the graph through some queries. I'm going to define queries in a few moments. As I said, there are a bunch of related works, but probably the most related work is this one. All other works do not provide guarantees compared to the optimum, right? And this work only deals with the theoretical guarantee that they provide in this work is only for SVM, right? So for general networks, there is no approximation algorithm. So the goal of this work is to provide a polynomial time algorithm that has some provable guarantees compared to the optimum and works for general graphs and uses limited number of queries to the input graph. We look at this problem in two frameworks. The second framework is the usual framework for sublinear algorithms. You can sort of have a random access query to the edges, but you don't want to read all the edges. What we used in this work was only random neighbors of each node. So we can ask one node, give us one of your neighbors uniformly at random. So the second one, the second framework is used can model surveys, right? You go to someone and ask for like a few neighbors, right? In the first model, we can seed one node and see the adoptions, right? So we can give a coupon to someone, give a coupon code to someone, and that guy can go and spread that coupon code, right? So we can track the people who use that coupon code, right? So the first one is like a more simple query setting. So this is an example of the spread queries. If we seed the red node, these guys are going to get adopted. But we don't see the edges between them, right? If we give a coupon to someone, we don't know who this, like, we know who uses that coupon, but we don't know who gives this coupon to whom, right? So we only see the ID of the nodes that are adopted using this coupon code. Okay, say we are looking at say the whole network is a star, right? And we don't know the network. If we seed one node, the whole network is symmetric, right? So if we seed one node, it's with high probability one of the leaves of the star, right? And say the probability of adoption is very low. Then with very high probability, we are going to see one edge, or probably even only one node, right? And we never see the center, right? With very high probability, if we don't want to seed everything, right? So we sort of need to see the relation between these adoptions, right? If we seed some of the leaves, the first node that's going to be adopted after this leaf is the center, right? So if we know the graph is a star, if we look at the intersection of these adoptions, we are going to see the center, right? So we need to look at the ID of these vertices. We cannot use the structure of these nodes. Even if we see the edges between them, we cannot sort of use this structure. But we can use these IDs and see the intersection between these IDs to see the node. And like looking back at the stars example, when we are seeding the nodes, when we are querying using spread queries, we are going to query the leaves, right? But at the end, the solution is the center. The node that we should seed is the center, right? So the solution is not necessarily one of the examples that we tried. So I'm going to show the algorithm in the next slide, but the guarantee that we provide is that using k squared, when we want to seed k nodes, using k squared number of queries, O tilde of k squared number of queries, we can have a 1 minus 1 over E, somewhat 1 minus 1 over E approximation algorithm, right? So if you want to only seed polylogarithmic number of nodes, we only need to use polylogarithmic number of queries to find the almost optimum solution. Okay. Say if we seed this red node, we see this this subset is going to be adopted. And if we see this blue node, this subset is going to be adopted. And if we see this orange node, this subset is going to be adopted, right? We look at the intersection of these adopted sets. And we say that the node that is in most number of connected components is the node that we should seed in this round, right? So the value of each connected component at the beginning is the number of vertices in that connected component. And the value of one node is the sum of the value of connected components that this node belongs to. Okay, this is for the first round. After that, if we see that one of these connected components contains one vertex that we already seeded, the value of that connected component is 0, right? So we show that this algorithm roughly follows the greedy algorithm. And we show that it's almost 1 minus 1 over approximation. The actual approximation, the actual number of nodes that's adopted is 1 minus 1 over e times optimum minus epsilon n. We have some like additive loss. But we showed that this additive loss is sort of necessary by showing that there is no constant approximation algorithm using less than order of n spreading queries, right? And the example is very simple. We have one clique of say size logarithmic, and all the other vertices are isolated vertices, right? So the optimum solution is to find one, is to seed one of the nodes in the clique, right? But with high probability, if we use less than n over log n nodes, n over log n spreading queries, with high probability, all of these queries are going to be on isolated vertices. So all what we see is some isolated vertices, right? So we do require this like additive loss. Okay, I'm moving to the second framework. Now I'm not using the spreading queries anymore. I'm using edge queries, but the techniques are sort of similar. In edge query, in this framework, we can query each edge, like or we can like ask one person, one of its neighbors uniformly at random. We are going to construct a subgraph and then sort of find the optimum solution on that subgraph and use it for the actual graph. So here we subsample some vertices, say all these orange vertices are subsampled. And then we simulate the adoption process from these selected nodes, right? And if size of the connected component of each of these nodes is getting very large, we stop. We don't go like very large. And then we do it for like a few other subsets, and we sort of combine all of these. Okay. Then to solve the problem, we again like we use the similar process to the previous one. For each node, we look at that node in all of these subgraphs and sum up the size of the connected components in these subgraphs, and that's the value. Then we use greedy algorithm. We greedily pick these seeds. We could show that we could like show a sort of linear time algorithm for this problem as well. Okay, so the guarantee that we provide is again 1 minus 1 over e times opt minus epsilon n, and the number of edge queries that we used is p times n squared plus square root p times n to 1.5. Okay, here we are using p times n squared, where p is the probability that one edge is getting like selected. So it can, when p is large, when the probability of adoption is very large, it's going to be n squared. But we showed that this is necessarily by showing that there is no omega, and there is no mu approximation algorithm that uses a subquadratic number of edge queries in general. So the only hope is to solve the problem when p is very small. And yeah.